Hello, my name is Reed Backus. I'm joined here with Brendan Mowers, Nolan Bainbridge, and Luke Greiser, and we're presenting our final presentation on the 5-claw gripper. The 5-claw gripper is an end-of-arm tool that's used to assemble parts, and the one that we chose is an electromechanical example of that. Shown here is our 5-claw gripper along with a exploded view of the gripper. And the primary and secondary customers for the 5-claw gripper is the automotive industry and electronics industry, which both use the grippers in similar ways. Here's a functional analysis of the 5-claw gripper. The overall function is to manipulate objects, and this includes holding and releasing objects, which also then include adding force, contacting an object, and then releasing force and adding clearance.
This is our functional component mapping matrix. As you can see, each part is matched with at least one terminal sum functive, which verifies our fast diagram. We added reduced clearance and fixed orientation to capture the full functionality of the part.
This is our product family design tables, one for functional differentiation and one for component commonality.
Here you can see our two variants for our primary and secondary customers, along with the common platform that allows for easy installation of the modules. And here you can see our modules. On the left is our primary variant, and on the right are our secondary variants. On the top, you can see our original assembly sequence. On the bottom, you can see our assembly sequence optimized using delayed differentiation.
Here's our manual assembly table with manual handling and insertion codes, as well as times for each part. The manual assembly efficiency for the original design was 44.2%. We selected a platform part, the carpal knuckle, and a module part, a claw bone, to redesign for faster manual assembly. We selected the carpal knuckle due to its high assembly time and lack of locating features, and selected the claw bone due to its high to assembly time and unneeded fasteners. Here's the original carpal knuckle and the redesign. We added snap fit holes to connect with the claw bone, so there's no need for the set screw. We added a lip for easier hole alignment of the carpal connector and also the carpal tendon. Here's the original claw bone and the redesign. We removed the right and left claw caps and added a fillet along the edges. We eliminated the dovetail design and need for the set screw, and it was replaced with snap fits. And the snap fits also allow for Z assembly of the claw bone. Here's our manual assembly table with the redesigned parts. The efficiency increased by 10% to 55.6%, and the manual assembly time was reduced by about 160 seconds.
In terms of design for automated assembly, the following platform assembly was chosen with a claw wrist, carpal connectors, carpal knuckle, and press pins. This includes only platform parts with geometries that allowed automation. The parts have a common function of adding clearance for gripper mobility, and parts highlighted for elimination or redesign are optimized within this subassembly and can be seen on the right. The two parts we redesigned were the claw wrists and the carpal connectors. The specific changes included reducing the fastener count by 5, as well as combining the connectors to further reduce the part count. We included a chamfer on the wrist in order to orient during automated assembly, and then added a feature to locate the connector and fully constrain the connector. The tables shown here break down the cost by handling costs, insertion costs, and total assembly costs before and after redesign, and a 30% cost reduction can be seen.
The next few slides will go through our process selection for the carpal connection, which functionally attaches the knuckle to the wrist, allowing for 1 degree of freedom, and the critical dimensions were found to be the hole spacing and the gap width. Here you can see our material and shape matrices, our mass and thickness matrices, our tolerance and roughness matrices, and finally our batch size matrix. Our final recommendation is sheet forming for manufacturing. Next, we will go through our process selection for the carpal knuckle, which functionally acts as a pivot for grippers, as well as the platform for the modular claw bone. The critical dimensions were found to be the hole spacing, the hole width, and the snap fit hole sizing and spacing. Again, here are the material and shape matrices, the mass and thickness matrices, the tolerance and roughness matrices, and finally the batch size matrix. And our final recommendation is injection molding for the carpal knuckle.
We're now going to go over the design for manufacturing for the carpal knuckle, which was designed for injection molding. Shown here is the design changes that were made for injection molding. This included designing with the guidelines DfM2, DfM3, and DfM4, and was implemented by adding a pocket with a draft angle, adding fillets throughout the material, and removing excess material to keep uniform wall thickness. By doing this, the material cost was lowered, as well as the operating cost and the die cost. Those two were only slightly lowered due to the additional surfaces that need to be included in the die. Other features for DFA were maintained to maintain the assembly and product function, and the pocket was small enough to maintain the structural integrity of the part. The vertical pockets cannot be removed because they are necessary for snap fits. Shown here is the design for manufacturing for sheet metal working, and this is the DfM Pro that was used to guide that. DfM 6, 8, and 11 were used as guidelines to improve the design for manufacturing. This included adding fillets for sharp corners, decreasing the thickness to increase the radius to thickness ratio for the bends, as well as adding ovals to avoid align features. These design changes reduce the material cost, but increase the operating and die costs due to the oval shapes. The internal profile was maintained to mate with the knuckle and maintain the assembly time. Oval holes also will reduce the amount of parts rejected, but they may lead to a looser fit and then change the part function slightly in that way. Shown here is the analytical versus the hubs cost for the sheet metal working part or the carpal connector. There's possible reasons for the discrepancies between these costs. That includes the fact that the analytical method uses antiquated values and doesn't consider the bulk pricing for materials. Also, the operating costs was at a baseline already for the analytical method. So the after design manufacturing costs cannot be lowered.
And here's our suggested product service system, which is a waste reduction program that allows customers to return old and unusable components as a down payment for future purchases, allowing for reduced replacement costs, as well as allowing customers to keep up to date with the products. And environmentally, it incentivizes recycling and also reuses old materials rather than sourcing new materials.
In conclusion, the final part redesign resulted in the cost decrease shown in the updated bill of materials shown here. This led to a total product cost reduction by 56%. In terms of design critique, we noticed that the part consolidation during DFA also reduced manufacturing costs, which was a pro. Some design changes included increased manufacturing costs. However, there was room for further part consolidation and redesign for cost reduction, which was another con, and alternate approaches in order to kind of fix these things is to do another round of DFA for the subassembly, including the carpal extenders, and then just to focus on the most expensive parts for redesign and how these can be reduced. We will not take any questions at this time.